Section 4.4. In this section, we discuss the following systems of differential equations. X prime is equal to f of xy, y prime is equal to g of xy. And we will try to graph solutions of these systems. Here is what I mean by that. Please take a look at a particular case of such a system. Here it is. X prime is equal to negative y prime is equal to x. By the way, we perfectly know how to find all solutions of this system. It's written in appendix number 1. Please take a look at this. Here's our system. And then in order to find all solutions of this system, we apply the standard procedure. We start with the matrix of this system. Then we find the characteristic polynomial. Since eigenvalues are complex, we choose only one of these eigenvalues. We replace lambda by I. We apply elementary row operations in order to come up with a reduced echelon form. We switch to the corresponding equation. And here is a complete description of all eigenvectors corresponding to lambda is equal to I. Then we apply the formula e to lambda t times v. So this is a particular complex valued solution. And then we apply Euler's formula in order to rewrite this as the sum of two pieces. This is particular solution number 1. This is particular solution number 2. So particular solution number 2 is cosine t sine t. Means x of t is cosine, y of t is sine. It's exactly what we have here. X is cosine, y is sine. Now, in order to graph this solution, let us consider the following triple. T, x, y. So if we replace x by cosine and y by sine, we'll get the following triple. T, cosine of t, sine of t. I claim that the set of all such points trace a helix in three-dimensional space. Here's why. Note that for any fixed value of t, since x is cosine and y is sine, and because cosine square plus sine square is 1, for each fixed value of t, the corresponding point on this curve will be a point on a unit circle with a center at the origin. If we cut this curve by the plane, which is orthogonal to the t-axis, means which is parallel to the xy plane. So once again, fix some t. Cut this three-dimensional curve by a plane that goes through this point and which is parallel to the xy plane. We'll get only one intersection point. This intersection point is a point on the unit circle with the center at the origin, because x squared plus y squared is equal to 1. Now, when we change t, this point will go along the circumference of this circle. Therefore, our curve is a helix. Now, for the same reason, if we consider the projection of this curve on the xy plane, we'll get the unit circle with the center at the origin. And now terminology. we call the xy plane face plane. We call the projection of our curve on the face plane the orbit or the trajectory. So the orbit of the solution of our system is a unit circle with the center at the origin. Any questions about example 1?
If you scroll to the appendix, Mr. Kirill, so if you scroll down, so I understood that x is equal to x2 I and 1. It's an eigenvector, and then very shortly after it says consequently that it's equal to e to the power of it, and then in brackets I and 1. Where did the e to the it come from?
So we apply the standard procedure. Let me go back to first section 3.8. According to section 3.8, a particular solution can be written as e to lambda t times v. In our case, a lambda is I. This is how we come up with e to it. A lambda is I.
I see. Okay.
Like this. And v is this, according to what is written here.
Okay. Yeah. Okay, I got it. Thank you.
So most important thing, the orbit is the projection of a three-dimensional curve on the xy plane that we call face plane. Here's example number 2. Consider this system of equations. In appendix 2, we show that its particular solution is this. Now, if we square both sides here and square both sides here, and then add the resulting equations, left-hand side will be x squared plus y squared. Right-hand side will be e to negative 2t because we square, and then in parentheses, cosine squared plus sine squared. Since cosine squared plus sine squared is 1, the right-hand side becomes e to negative 2t. So, if we square both sides here, and add up these two equations, on the left-hand side, we get x squared plus y squared. On the right-hand side, e to negative 2t. This curve is a spiral that converges to the origin. Here's why. Remember, the right-hand side is e to negative 2t, which means if t increases, if t goes to infinity, e to negative 2t decreases and goes to 0. Observe that for any fixed t, our equation is an equation of a circle of radius e to negative t. We basically consider the set of points. Each of these points belongs to a circle, and the radii of these circles decrease and go to 0. Thanks to this, we trace a spiral that converges to 0. Guys, any questions here?
Can you re-explain how you know it looks like a spiral again?
Well, let us try it in a different way. Think about this. Fix some t. For example, put t is equal to 0. If t is equal to 0, the right-hand side here will be 1. The right-hand side here will be 0, correct? So we'll get a point with coordinates x is equal to 1, y is equal to 0. We will get this point, correct?
Yes.
Now, let us increase t. Let us put, for example, t is equal to pi over 2. If t is equal to pi over 2, sine of pi over 2 is 1. Cosine of pi over 2 is 0. Agree?
Yes.
So if t is pi over 2, x is 0, y will be e to negative pi over 2. Correct?
Yeah.
So we will get this point and observe that this distance is 1, this distance is e to negative pi over 2, which is lesser than 1. So this distance is lesser than this. Agree?
Yeah.
Keep going. One can see that if you plug in t is equal to pi, we will be here, and then this distance will be even smaller than this distance, and so on.
Okay, cool.
So in these two examples, we trace the orbit using college algebra and trigonometry tools. In example number 1, we managed to exclude t completely. In example number 2, we excluded parameter t partially. But anyways, in these two examples, we applied only college algebra and trigonometry tools. In the second part of this handout, we use a totally different method. So this handout, guys, consists of two parts. Part number 1, we exclude t completely or partially using college algebra or trigonometry tools. In part number 2, we will use calculus. Let me go back to this. So we click on calculus and chain rule. Please take a look at this formula. dy dx is dy du times du dx. This is chain rule. In our case, let us replace u by t. So if in this formula we replace u by t, the formula becomes dy dx, which is exactly over here, is equal to dy dt, which is here, times dt dx, which is here. Now, let us think about dt dx as about a normal algebraic fraction. As we discussed, we can do it if we think about dt and dx as about differentials. Now let us use college algebra. When we multiply by dt divided by dx, it's same as we divide by dx divided by dt. Lastly, observe that dy dt is g of xy. Dx dt is f of xy. Conclusion, dy dx is g divided by x. It's exactly what is written here. Here's an example. Let us consider this system of differential equations. Note that we do not know how to solve this system because this system is nonlinear. We have x squared, we have y squared. But we don't really need to solve it in order to find orbits. Instead, let us use this formula. Dy dx, which is on the left-hand side, is dy dt, which is x squared, done, divided by dx dt, which is over here, done. Lastly, observe that dy dx is equal to x squared or y squared is a separable differential equation. We show how to solve it in Appendix 3. Here is the general solution of our equation. Therefore, the orbits of this system are the set of curves y is equal to cubic root of x cubed plus c. And now, in order to sketch these orbits, you can use, for example, Wolfram alpha. Let us go to Wolfram alpha. So we type in plot y is equal to x cubed plus 1 to the power 1/3. And here is a particular orbit. Any questions here?
Wait, can you reiterate what the significance of an orbit is?
An orbit allows us to visualize solutions. An orbit is a projection of a three-dimensional curve on the xy plane. So if we consider a particular solution of this system written as x of t, y of t, and consider the following triples, t, x of t, y of t. These points will trace a three-dimensional curve. If we project this three-dimensional curve on the xy plane, the resulting two-dimensional curves are graphs of these equations. Was that a question?
It was, yeah, thank you.
Here's another example. We have a system of differential equations. We apply same idea. dy dx is equal to dy dt, which is this, over dx dt, which is this. We cancel out the common term, and the resulting equation is a separable equation. We solve it in Appendix 3, Part 2. The general solution is 1/2 y squared plus x squared is equal to c squared. So the orbits of our system are the families of ellipses. Any questions?
Professor, would you mind redoing the last example we did?
Are you talking about this example?
Yes.
So we apply this formula. By this formula, dy dx is equal to this, which is over here, divided by this, which is over here. We cancel out the common term, and the result is negative 2x over y. Now, what we see in front of us here is a separable equation. Please take a look at Appendix 3. In order to solve it, here is this equation. We move y to the left, dx to the right, done. We integrate both sides. Antiderivative of y is y squared over 2. Antiderivative of 2x is x squared. And lastly, if we move negative x squared to the right, we get exactly what is written over here. This one. The graphs of these equations are ellipses. Did I answer your question?
Yeah. Also, why is c squared?
Let me start with an equation of a circle. The standard way to write down an equation of a circle is x squared plus y squared is equal to r squared. So basically, we follow the same pattern here, and we put here c squared.
Okay, sure, that makes sense.